I'm Yuejilin. Here I'm going to show you the solution of question 1 in homework 10. Question 1 asks us to collection the definition and some simple properties of the examples of some stochastic processes. First, let's have a look at the first one, that is the Poisson process. Poisson process. The definition of Poisson process is the number of n t1, t2 of the points ti in the interval between t1 and t2, and the length of this interval is t2 minus t1. This is a Poisson process. Is a Poisson random variable with the parameter lambda. The expression is in like this expression, and if intervals t1, t2, and another interval t3 and t4 are non-overlapping, then the random variables n of t1, t2, and n of t3 and t4 are independent. At the time moment of t, that equals t1 minus t2 minus t1, there is more than one Poisson process if we use the points ti to represent it. We can from the process x of t equals n of 0 to t, and we can get the figure of this Poisson process is like this. The x-axis is represents t, and the y-axis represent Poisson process, that is x of t, and the figure is like this. And another properties of the Poisson process, that is the first order probability mass is equals p of x of t minus k will equals the e minus lambda t's power, and multiply lambda t's k's power, and divided by the k, divided by the factorial of k. And the mean of the Poisson process is the expectation of x of t in equals lambda multiply t, and the autocorrelation of the Poisson process is equals r of t1 and t2. That will equals lambda square multiply t1 multiply t2 plus lambda multiply the minimum of t1 and t2. Now let's come to the Poisson increment. The Poisson increment is defined as the y of t equals x of t plus epsilon, and minus x of t divided by epsilon. X of t is a Poisson process. The properties of this Poisson increments is the first order probability mass is p of y of t equals n divided by epsilon equals is minus lambda multiply epsilon's power, and multiply lambda multiply epsilon's n's power divided by the factorial of n. And the expectation of the Poisson increment is lambda, and the autocorrelation and the autoconvergence is shown as these expressions. Something interesting is that the Poisson increment process is a good tool for us to, or a preparation for us to understand the Poisson impulse process. We can have a look at this expression. The expression of this part is have a look at this. The figure of this part is a triangle area, and the area will be lambda, and is independent of the epsilon. When epsilon gets to 0, and the triangle will the triangle will becomes an impulse, and the area of the impulse will be epsilon. Will be lambda. The third one we need to figure out is definitely the point impulse process. The definition of the point impulse Poisson process is z of t equals the differentiation of x of t. The definitely x of t is a Poisson process, and the figure of this point impulse process is like this. Several impulse, and the x-axis is t, and the y-axis is z of t. And now let's have a look at the properties of the point impulse Poisson process. The probability is probability mass and has no definition, and the mean will equals expectation of z of t will equals lambda, and the autocorrelation r of t1 and t2 will equals lambda square plus lambda multiply delta of t1 minus t2, and autoconvergence will equals c of t1 and t2 equals lambda multiply delta of t1 minus t2. It's just this part. In our daily life, we may see the point impulse process like some short noise, just like the impulse and nearly an impulse like this, and several times. It's like the short noise. It's some impulse in some very short intervals of times like this. Now let's come to semi-random telegraph signal. We also define this process based on the Poisson process. Suppose x of t is based on the Poisson points, and the number of the points in the interval t1 between t2 is a Poisson random variable with this expression, and x of t is equals 1 when k is an even number in 0 to t, and the x of t equals -1 when x is an odd number in 0 to t. And the first order probability masses of this process will have two values. That is, when x of t equals 1, the probability will equals minus lambda t's power multiply lambda t's power plus minus lambda t's power divided by 2, and when x of t equals -1, the expression of the first order probability masses is like this one. And the mean and autocorrelation and autoconvergence is shown as the below. probability of x of t equals 1 is not 0.5 because we started with 1, and it will be a little bit higher than 0.5, and it will the value will equals 1 minus e minus 2 multiply lambda t's power divided by 2 will goes to 0.5 when t is goes to infinity, which and the mean when t goes to infinity, the mean will the mean of this process will goes to 0, and when t1 minus t2 goes to infinity, the autocorrelation will goes to 0. That will matches to our knowledge, which is that when t1 and t2 far away, x of t1 and x of t2 are less, and will have less probability to correlate it. Now let's come to the fifth question, the random telegraph signal. The definition of this process is y of t equals a multiply x of t. The definition of a is that p of a equals 1 and p of a equals minus 1 equals 0.5, where x of t is a semi-random telegraph signal, as we have shown before. The first order probability message of the process is p of y of t equals 1 equals p of y of t equals minus 1 equals 0.5, and the expectation of the process equals 0, and the autocorrelation and the autocovariance equals are all equals is minus 2 multiply lambda multiply the absolution of t1 minus t2's power. For this process, the special one is that the first order probability mass is all equals 0.5. That it's that this shows that y of t might be a street sense stationary, and also the expectation of y of t is a constant. That might let us think the process might be an SSS. Let's come to the sixth question, is that the definition about the random walk. That is when we toss a coin for many times, and the k will equals the number of heads in the n times tosses. X of nt will equals k of k multiply s, and k multiply s subtract n minus k, and multiply s will equals 2k minus n multiply s, and the first order probability mass is equals to this expression, and especially the mean of this process is equals to 0, and the autocorrelation and the autocovariance are the same, equals to this expression. In this process, we can guess that when n goes to infinity, we will have a Gaussian density, and in look at the autocorrelation function. It contains a part of the minimum of n and m, and it looks like the expression we've seen in the property of the independent increments. Now let's come to the Wiener process. The Wiener process is the limitation of the x of t, and that is the limitation of the random walk. When talking about the properties of the Wiener processes, we can get the first order density function is like this one, and also the expectation of the Wiener process is 0, and the autocorrelation and the autocovariance are the same, are all the minimum of T1 and the T2 multiply the alpha.